Your ranker can look fine in training and still fail in production because the labels are noisy. I'll show how to spot and clean bad judgments in Python. This is the pattern you'll be able to implement by the end, which flags noisy judgments and cleans labels, then reports the ranking quality lift. I'm Professor Pi, teaching search and IR with simple Python. Label noise in learning to rank is a practical pain. You train a model on human grades or click data. The model learns those signals. If the signals are inconsistent, the model learns wrong preferences. In production, you then see poor results or user complaints, even though offline metrics looked okay. At a high level, we want two things. First, find where judgments disagree or contradict a simple baseline. Second, combine judge credibility into a cleaner label set and retest the same ranker. That gives you a measurable lift or a clear reason to relabel. We will build a tiny, concrete example you can run quickly. It uses a small query and 5 toy documents. We simulate multiple judges, spot disagreement, weigh judges by reliability, produce cleaned labels, and then tune a simple ranking bonus. This keeps the ideas focused and shows how the cleaned labels change NDCG before we move to bigger data. Now we create the tiny dataset and measure baseline quality. This snippet builds a tiny query document set, ranks by exact term overlap, and reports NDCG at 5 against noisy labels. The dictionary docs holds 5 short documents, and queries defines a single query with 2 terms. The mapping Y contains per document graded relevance for that query, intentionally including one stale or wrong judgment. The function NDCG computes NDCG at a cutoff by comparing discounted games to an ideal sort. The expression rank sorts document IDs by counting how many query tokens appear in each document. Finally, the print shows the NDCG at 5 for this naive ranker and the top document ID. The result quantifies the starting point under potentially bad labels. Next, we scan annotator grades to find obvious disagreements. This example flags suspicious labels by scanning annotator disagreement for 1 query. The nested mapping labels stores 3 judges' grades per document. The comprehension RNG computes, for each document ID, the difference between the maximum and minimum grade across judges, a simple proxy for label conflict. The call to max selects the document with the largest range, using the keys shared with the earlier Y mapping. A larger range means the item likely has inconsistent guidance for training or evaluation and deserves review. The printed ID and range tell you exactly where disagreement is highest, spotlighting a likely noise source. Now, we estimate which judge aligns best with the simple lexical signal. This code estimates annotator reliability by how consistently each judge agrees with a simple lexical order. The dictionary stores the overlap score for each document using docs and queries. The list pairs enumerates ordered document pairs, where the lexical score prefers A over B. The function rel computes 1 minus the fraction of discordant pairs for a judge, where their labels would invert the preferred order. The mapping W holds these per judge consistencies, and max retrieves the most consistent judge. If you enlarge the document set, this metric becomes more discriminative. The printed judge and score show who aligns best with the baseline signal. Next, we use those weights to make a clean target and reevaluate. This snippet consolidates noisy judgments into a cleaner target and rechecks ranking quality. The variable W from the previous step gives a reliability weight per judge. The comprehension clean computes a weighted average label for each document ID in Y, dividing by z, the sum of weights. The list rel C aligns these cleaned labels to the existing rake order from the lexical baseline. Finally, NDCG at 5 is recomputed with NDCG, and the print also shows how many items moved substantially relative to the original Y, a threshold of 0.5. The higher NDCG indicates that the same ranker looks better under denoised supervision. Lastly, we try a small tunable change to the ranker and pick the best setting under cleaned labels. This example tweaks the same lexical stack by adding a tunable IDF bonus to matches. The list terms comes from the query. DF counts document frequency per term, and IDF turns that into a mild boost. The function rake alpha rakes documents by summing 1 plus alpha times the IDF for each matched term in a document. The list cans defines a tiny search space for alpha and best picks the value that maximizes NDCG at 5 against the cleaned labels clean. Larger alpha increases the influence of rarer terms. Smaller alpha reduces it. The printed NDCG and alpha show the best setting for this query under cleaned supervision. To map this toy to a real project, think of the 5 documents as a sample shard of your production index. The same steps scale. Compute a simple baseline score for a sample of queries. Gather multiple annotator judgments or split click data into pseudo-judges. And then compute judge consistency against the baseline. Use those weights to produce a cleaned training set and to validate model or parameter choices. On real data, you would compute these stats across many queries and use aggregated improvements to decide a full relabeling or targeted review. Recap. It spots label conflict by range across judges, weighs judges by agreement with a baseline, and averages labels to reduce noise. Use this when you suspect inconsistent human grades or weak click signals. One caveat: the baseline you pick biases which judges look reliable, so choose it to reflect real relevance. Next step, sweep the alpha bonus across a larger query set and pick a global value that improves NDCG under cleaned labels. If short practical IR helps, subscribe and watch the IR videos.